it's audible, Rana.
Yeah, ma'am. So can you share my slides or I?
Sir, you can share your
You
screen,
can
sir.
share your slide.
Is it? I think is it visible?
Yeah, is
Okay.
it visible? It is visible.
It is visible, sir.
Okay. So the title of what we are going to discuss today, like the photon statistics and quantum phase distribution in the current optical link in the presence of phase noise. So the outline of the talk will be like I will discuss the basics like introduction of quantum mechanics and quantum optics, and this will give the fields that how it can be applied to the quantum key distribution system. Or here we have done the application in frequency coded FCQKD system, and then we'll go to the quantum theory. It means the discretization like photon statistics and semi-classical theory of direct detection in optical links.
Yeah, Rana,
Similarly,
sorry for the interruption. Rana, your voice is not that audible, I think. What about Anish, sir? What's your
audible?
opinion?
Ma'am,
Is it clear, sir? Clear
somewhat
or
okay.
it's like
Somewhat okay, ma'am. Somewhat only okay. So, sir can check with the.
Okay. Is it now? Is it okay, ma'am? Somewhat? Or I have to change the place?
now it's okay. Now it's okay.
It's audible, ma. No problem. Everything is okay. Fine, comfortable.
Oh.
Okay then.
Then next part, I will go for the quantum theory. Like we will see the photon statistics and semi-classical theory of current detection for the optical link, and we will conclude to the research part of that. So starting, we will go with the first. We'll see what is the quantum statistics. Some of the fundamental postulate of quantum mechanics are as follows. So before starting, we should know that what is the state. Like generally we have a kit. Can you see the marker? Like is it visible? No. So it is like we have the state. Like I have written the Dirac notation like psi. So hold the information of particle information and call it the wave function also. So psi represents like how we see the electric field. If you see in the electric field, you will write E of RT, means it is a position with time. You will get E naught cos omega t minus beta z. So it is a function of t and z. So it means that electric field have the information of position and time. Similar way, if you say the state psi, it means that it holds the whatever generally we say in quantum mechanics particle. So it holds the information. So first thing we should understand that psi, it have the particle information, and its notation by Dirac is called fit or wave function. And another thing, the measurement psi is have a complete value, and here okay. So the state psi specify the probability of various possible outcomes. When you say the psi, it means that it talks about the probability, and when you talk about the probability, it is measurable by the experiment, by state itself. So, and other thing, what is observable in the case of quantum classical mechanics, you can so in classical mechanics, any physical variable, when you talk that, you will say that momentum or position. So any given position, if you say like you have a scalar quantity x or the p have the momentum part, but in the quantum mechanics, it is called as a operator. So here we will say the position operator and the momentum operator, right? So this is the two things. So when we say the quantum statistics, we should understand how to represent the state and how it is given the observable, that is operator. Now, once we know that it is okay, what is the quantum state, and then we will get what is the normalization. So generally, we have the psi and alpha. Psi, you can say it is just some of the physical state. So alpha is here, you can represent as a complex number, and you can see the mod kit and adjoint of kit mod whole square is 1. It represents like orthogonality, right? It is like when you say the like a function, you have orthogonal I, X and Y. So that is make Dirac equation 1. And another thing, we have a once the probability is same, that's why the normalization comes in the picture. Second is the superposition principle is there. So if you have kit style, you have a kit type 1 and type 2 are the two kits and in Hilbert space. And generally, if you have a total size, it can be represented in the form of alpha type 1 and beta type 2. So how it can be viewed, right? So if you see the, sir, can you remove me the admitting option and all, because it's coming my screen. So it's okay. So you can see that here bit, if you have bit 0 and bit 1, so if you, it can be represented in the combination form like size. So size, for example, you can see that alpha bit 0 plus bit 1, it is a beta 1 bit, right? So it is okay. Why is it? So the qubit, if you see that the combination, if you see that a psi, it is a linear superposition of bit 0 plus beta 1, and it is the qubit, right? So when you write, suppose I want to observe only bit 0, so this orthogonality, the probability will be coming alpha, mod alpha square. So when we take orthogonality, and similarly, if you want to observe bit 1, it will come mod beta square. So similarly, another example of superposition, if you see here, alpha 0, if you have right circular polarization and left beta for bit 1, so when you see the combined linear position of psi, it looks like the down picture. You have seen that up and down arrow, that is equal to alpha bit 0 and beta 1. So here we are getting the familiar of two things. We have a state that keeps all the information of position and time. Next, we are talking about the operator. So like in the previous slide, we have shown that we have a position and momentum where we are operating as a operator. And there is also, we have the basis of a space, like you have orthonormal kits. So suppose as example, in current, we are having three-dimensional space. So this is n equal to 3, I, x, y, z. So 3 orthonormal bases. But in quantum mechanics, you can study the Hilbert space of n dimensions, and all can be represented in the linear combination of the basis space. So we will see more about the operator also. So now whenever operator it have a mission operator, you can have the acting on the state. Like if you, in example, you can see that any operator, it will act on the state. It will give me the eigenvalue, that is very real value. And that's why means what it means that if you have any operator, it will act on the kit, it will give me the physical variable, that is a measurable quantity, and then will give me the time kit. So that is one important thing is there. Another thing is non-commutation principle. That is what is a non-commutation means. If you have a two operators, so we can write the commutation principle A and B. So we can write equal to A operator B minus B operator A. So it will be in quantum mechanics, it will not be always will be the same. It will be not equal to 0. But if you see the classical mechanics, when you write the commutation of x and y, you are always x into y, y minus x, it will always equal to 0. And this leads to our uncertainty principle that we know that to identify position and momentum must be slide h by 4 pi like h bar by 2. So it means that the commutation relation is very, very important for each point of the link. If it is, we cannot write A, if it is not equal to 0, you can't write like commutation A, B equal to minus B equal to minus B operator, or you can say hat, A hat, right? So this is a very important what ordering you are writing in the quantum mechanics and quantum optics, or when you are doing the quantum analysis. So still we to take a point from the last slide, we understood that we have one wave function that is a kit that we can say like a wave function that electric field, position and time. There we have a operator that will act on my kit, that is a wave function. It will give me the eigenvalue, that is my physical operating operation. And another part we have seen that like always we should apply the non-commutation principle in the link. And another very important thing is that how to solve the problem in our optical link. There either we have a three pictures like Schrodinger picture, Heisenberg picture, and interaction picture. So generally we will just I'm saying here like start with the Schrodinger picture. Here this the information you can see in the equation I h bar dou by dou t mod psi t, and h, it is here h is nothing but operator acting on the kit psi t, right? So psi t is nothing but we are keeping the information all the time information, position information contained in the psi t, whereas h it does not have any information. So Schrodinger picture, when we solve the problem, that means the kit, when we say the wave function, contains all the information, whereas the operator here, h we have written, that contains no information. It will act like the operator, it is independent of the other information. So h you can say here, like when you write the Schrodinger picture, h is written as a refer to the total energy of the system. And total energy of system generally we write in the like of P square by 2m and V. So P square by 2m also can be written like half mv square, that is the kinetic energy, plus V. V is nothing but potential energy, right? So it can be different. So whenever you define any system, Hamiltonian will be the total system, total energy of the system when you represent it. So you can see the once more the time development of quantum state, I h bar dou by dou t, and the wave function contain my information. Here the operator is h that contain my total. You can see that here h equal to p operator by 2m. So this is have a kinetic energy, and v operator it have my position information acting on psi t, and it will give me eigen energy value, that will be the energy of the system. Then another picture it is very useful for our quantum optical link to solve the problem. That is Heisenberg picture. Here the information is not in the state, like you don't have any information, but information is present on the h. So that's why it says that the operator carry time dependence where the state vectors are time independent. And the Heisenberg equation of motion, you can see that IH, the operator A by duty, and it commute with the operator with the energy of the system. So this is one of the important picture because in our optical link that we have the laser, channel, and the detector. So the field operator evolution is governed by Heisenberg picture. But then if you see the interaction picture is nothing but harmonic picture of Schrodinger picture and as well as Heisenberg picture. So here partially the state vector operator will also keep the information, and as well as state like if you have eigenstate, that will also keep the information. And we have that. So that is I will see more in that. Actually, interaction Hamiltonian, we can see that it is have the free space h naught and h of t, right? H of t is nothing but time dependent part of the Hamiltonian. It comes, right? So this is the just details you can go through that. But when we solve our problem, this whatever the analysis will fall in out of these three pictures. Then okay, once we know that we have one eigenstate here psi of s. If it is one eigenstate you are dealing, it is fine. That is a pure state. But if in the current scenario problem, you have the more number of quantum states. Means you have the multiple particles and acting on each other, and each particle psi 1, psi 2, it have the information of position and time. So how to deal with the mixture of quantum states, and that is taken care by that will be helpful by using density operator, right? So in the case of you have when you are dealing with multiple fields, that you have the multimode laser and multi amplifier, and you have multimode, you have the range of C band amplification. So you have more number of bands, then you can't solve like considering psi 1. So that time we need our density operator will be very useful, so that it is have a sum of here P S is nothing but probability of the given state psi. So suppose if you have psi 1 field, so probability P1 belongs to psi 1, P2 belongs to psi 2, and this is my way of representing in the Dirac notation. And we should make sure that all mixture of state, it's the probability of occurrence of each state. So the sum of the probability lie between 0 to 1, and the whole sum will be there become 1. Suppose if you are considering only a single laser source, monochromatic laser source or any, that time density operator will be written that probability will be 1 here, and a probability will be 1 here, and you can see here that state size. And if you want to find the average, like average on the density operator, you can find with the diagonal operation kind of thing. So that's why the density, I am giving the feel that how the density operator is useful for our quantum, our optical link. And another very important thing given by our the standard in quantum statistics, they have taken like a single mode field, that is taken a laser source, and we in electromagnetic fields and antenna on every communication, with the help of boundary condition of electric magnetic and with the help of Maxwell equation, we can able to write electric field and magnetic field in the classical mechanics. So here, there we are writing electric field and magnetic field. You will see that it is a continuous time varying process, like sinusoidal varying, and you can see it is a electric field Z and T. It is a position and time. So here in quantum statistics also they have represented as a quantization of magnetic field. So quantization means the discrete level. I can count as a number of photons, or I can make the quantum level when you are talking about one number of photons, 2 photons, 3 photons. So their quantization is very, very important. And then we know this is a classical electric magnetic field, and quantum they have replaced like here Q of T, right? Generally, if you write electric field for plane wave equation, it will be have E naught cos omega t minus beta j and omega t term. So this is the Q of T they separated, and for magnetic field P of T separated. So in the case of quantum mechanics, I am giving the field that very concise result here. So electric field directly proportional to here Q of T. Similarly, magnetic field directly referent to the P of T, right? And the variable here Q and P are canonical variable. Canonical variable means here that of single mode field. I am talking here single mode means single frequency, right? So here the uncertainty principle lies here. So that commutation relation Q and P equal to I H bar. This is very, very important, the link here. So when you writing the electric field in the classically, when we read electromagnetic field, there we don't worry about this commutation relation. We assume that all QP, how it varies, we don't worry about that. But here, when you write electric field, it is associated with P of T. B, when you write, you associate with P of T, and it satisfies our uncertainty principle, and here Q and P act as a operator, right? So, and just for comparison, comparison with my classical, that's why we are using electromagnetic field theory. There, if you write the total inner electric field, you write the triple integration volume integral, half of epsilon naught Ex square and B square by 2 mu naught permittivity. So this is my, you can see the electric field, the energy comes from electric field, or you can say the Poynting vector, the energy what we are getting. So that will be the total energy of the single mode field come from the source, right? But here, if you see that in Hamiltonian, in the quantum mechanics, so for single mode, I can write like H, that will be half of P square by omega square Q square. So we can retain the Hamiltonian in terms of P operator and Q operator. And P operator and Q operator with some small mathematical relation, I can write here annihilation, creation, and destruction operator and the creation operator, that is A dagger, right? And once you understand that A and A dagger not commute each other, means commutation of A dagger, A comma A dagger equal to 1. So you can see the difference between the first equation here. Here the total energy of system, here written here E naught, and here in terms of P and Q. So this is a main, the energy here H hat. H hat is nothing but, you can see that it is Hamiltonian, right? And it is operator. And where A and A dagger is related to PQ and it is also written as an operator, right? And then let us see that, okay, once we know that and we know how to make, when you say the quantum, we mean that there classical, we talks about continuous, and when you say the quantum, we call as a discrete nature. Like we are studying in our signal system, discrete and discrete DSP, discrete point and continuous transform. So similarly here, when you talk about quantum in another way, we can think about as a discrete kind of thing so that you can count the number of photons in the case of photonic system I'm saying. So let's be whatever we gone through it. Now we are thinking like, okay, we have discussed about the single mode and through the electromagnetic field, we can able to write the operator. Operator means I can write H, that is the total energy of the system. And we are writing here potential energy plus kinetic energy, the summation here. And when it is act on N, I will explain you later also, but when you act on Hamiltonian taken and hit a state, it gives my energy eigenvalue and it remains the same state. So when you act as a acting on N state and give the energy of the N value and N state. So this we have studied in the 12th physics that what is the energy discretization of an atom case, what is energy level. So when you see that for N equal to 0, you can see that half H over omega comes. This is the spontaneous noise emission. So we leave that part. And then when you see that when N equal to 1, the energy of the Nth energy eigenstate, suppose given an N state, N equal to 1. So 3/2 H omega will be given the energy of the Nth state. Similarly, we can make N vary from 0 to infinite. So here, the word we are saying that we have infinite dimension. When you talk in the quantum mechanics, you can see from N to, you can talk about infinity. And each correspond to N equal to 0, you have eigenstate and H acting on eigenstate N having energy eigenvalue. So we can find each energy eigenvalue at each state, and that's why energy eigenlevel diagram is there. And to simplify that, there are given this notation like kit and that adjoint of the kit. And here, since you know that A, H, and P is related to my ladder operator, or you say the field operator, here it's creation operator. It means what? Then it is act on a state N. It means that one photon created. And energy eigenvalue, it is written plus a square root of N plus N. Similarly, if you have the position A, and this is destruction operator, so from N to N minus 1. So you can see there, you can see that even one photon, how it is creating and how destruction of the photon, it is happening in the energy in the single mode field case, right? And once we read this, okay, we got to know about the, now we feel that, okay, we are studying about the discretization of single mode field. So when you say the laser source, it is a monochromatic, and you say that, okay, this is my eigenstate, we understood the quantization. Now, how the question in always is come in mind, why we are going quantum? The first thing that why we need to study quantum. If everything working in the classical, where the quantum, the theory of quantum will work, and where the theory of quantum which doesn't, it's not required to explain the system. All right. So Glover is got Nobel Prize in the 2005 for the coherent state and the discovery of another formulation in the case in now in physics. And he said that, okay, there is a one coherent state in the, and it behaves like what was the behavior I have seen here, quantum linear harmonic oscillator, it behaves similar kind, and it is a classical state. So classical means when you write the coherent state alpha, so alpha gives me all information of the existing system in classical, reasonable classical limit. But same time, the same alpha, this alpha when you say it alpha when we talk here, we have a real part and imaginary part, we have complex values. And this A operator, this is destruction operator acting on coherent state alpha, the state alpha, we are getting alpha. This alpha is a real value. because then you take the reverse on that, A dagger, and it will give alpha conjugate. When you multiply taking average, alpha and alpha conjugate, you get mod alpha square. So mod alpha square is the intensity. So when we talk about the laser light comes from the laser, it falls on detector, and we talk the intensity. And intensity is taken care by mod alpha square. But this quantum state, what it says, we can transform this current state alpha into the discrete form, like the technical physics term, we then say the Fock basis representation. But we know DSP for electrical engineer, we understood like a discrete term from n equal to 0 infinity. So here we transform, here we are talking current state alpha into alpha conjugate intensity. But the current state alpha also expanded into the n state, like a Fock basis representation. So you can see here the current state in this upper line, it shows the classical, whereas in this case, that is the CN-10, it talks the quantum, right? And that's why the normalized current state, it is written exponent of mod alpha square A mod that T10. It's like when you say mod alpha, sorry, kit alpha, it will get represented into the quantum Fock basis representation, that is n. So that is the beauty of current state, and this is the main state we assume in the qubit or other places where we use entangled state and two photon state. So that time we should know what is the behavior of current state and how the A dagger, the left A and A dagger will work on that, and how the intensity works. And that's why I've written here, Glauber got Nobel Prize for optical coherent system, and he not only solved the coherent state, and coherent state is very ideal to the laser system. So when you say monochromatic laser source and you have a single mode and alpha represents a single source, eigenstate the given all information. And after that, he saw that we can not only current state can be used for the many other probability statistics to solve the many physics problems. So he gave like how we ever studied the density operator, and he gave the density operator we can also study in terms of current state representation. And the important part is like a P alpha. P alpha, what we are studying in probability function, like a P alpha is greater than or equal to 0, right? And probability sum, and this is also analogous to our like probability distribution function what we ever studied. But in the case of some quantum mechanics, it is a P alpha is a negative value. But if you study in our probability case, we never find the probability distribution function less than 0. But in the case of he solved in many behavior, we have seen the example in physics, there P alpha is a negative value, and that is called singularity and non-classical nature. So there you can't solve the problem with the help of classical mechanics or existing nature of the whatever you have the analysis. We cannot solve if P alpha is negative. Till P alpha is positive, we can solve somewhere if you for larger intensity in classical, but lower number of intensity you can't solve by classical field or semi-classical field. Semi-classical means some part we are taking as a quantum and some part is taking the classical, and that's why it's called semi-classical. To treat the non-classical behavior, means non-classical behavior, as I say, means that P alpha is negative value. There you can talk only on the quantum mechanics. And for measurement, now when you talk about the phase noise, like in our case of any kind of you have the generally when you talk about communication, we talk about intensity and phase, right? So we want to know that what is the difference in phase and what will be the intensity. So these all things will be done by the interference, right? And that there we taking autocorrelator, and then we take the Fourier transform and we get the spectrum, right? So in the case of classical, generally we do the Mach-Zehnder interferometer, and Brown-Twiss interferometer means what? You give the light into the mirror with the same length and it gets reflected back from the two end of the mirror, and you observe. You see at the observation do at the detector point, and you see that whatever the signals came, it overlaps each other. It means there is a noise in there, right? And but in the case of classical and quantum, he given the same classical we can transform into the quantum. So quantum, what he have done, he follow Heisenberg picture of electric field operator, and there in electric classical field you can write Ex into Ey or Ey into Ex. But in the case of quantum mechanics, you cannot write there. If you're writing, you have to follow some fashion. So I have considered normal order fashion. Here is dagger and a dagger kind of thing, right? So first we should know the first degree of coherence. First degree of coherence means you have the like electric field operator, here creation and destruction, and similarly you are taking the square root of that. If it is becoming 1, so it means that we don't have any noise kind of thing, right? So, but in our case, we are in the Mach-Zehnder interferometer or Brown-Twiss interferometer, we assume that light beam, like with respect to position, it doesn't change. Whatever you give the Gaussian beam, it remains the Gaussian beam at throughout the path travel. So it is the first order for, like you can see, correlation coefficient or degree of first order or photon correlation function, you can say in the terms of photon. You can see that T plus tau. So when you have one path, you give an extra time delay, and with time delay, so you get the first order coherence and the second order coherence. With these 2 degrees of coherence, we can get the autocorrelation function, and taking the Fourier transform, we will get the spectrum, and through a spectrum, we can observe the physical reality, how my thing means, how the intensity is decreasing, how my phase information getting disturbed. So up to this, I think we cover the basics of our quantum statics and quantum optics. And what we have said, just I want to recall from this diagram, we said that the coherent state is there. One, we have the ideal state, and we have the operator. So for keeping in our mind, like a Hamiltonian, like a total energy of the system, we take as an operator, and coherent state alpha, we represent as a eigenstate. And when you say the monochromatic laser source means you have the single mode frequency, right? And for single mode frequency, we alpha have the real complex value, real alpha and imaginary alpha. So for given theta naught, we have the given intensity. Suppose if it is like a pure coherent state, there is no noise. When you say the ideal laser, we don't have any noise. It means that it has the single point here, right? And single line will be there. There is no like randomness along the phase direction, right? So what will happen like that? If you then, as I told you that ideal I applied my quantum optics to the quantum communication. So ideally, inherently, if you take the laser source, the laser have the line width. You can't get a monochromatic laser. So it means that there is a phase noise already present in the laser source, right? So how to write that? Okay, once you have this is my ideal laser, alpha e to the power minus I theta naught, and when you add the phase diffusion of laser, alpha I theta naught I phi tau, it cannot be written very easily. I have written here I phi tau. It can be solved by Fokker-Planck equation and more other rigorous mathematical stuff. And then only you can write the red color e to the power I phi tau, because it is a Dirac notation. Once they define, you have to, because the kit, it keeps all information. So when you are writing inside anything in the kit, you should keep in the mind, or we should keep in the mind, like what are the information that it contains. And how we got like this? So we have, as I discussed like that, with the Mach-Zehnder interferometer, we taken the electric field at time t and t plus tau, and we calculated the first order correlation function. And when we see that first order correlation function, we get e to the power minus j omega naught tau and the phase term. When you take this Fourier transform, you will get the Lorentzian spectrum, right? So if you have in the case of laser, and they have the spectrum analyzer, OSA, optical spectrum analyzer, you will see that middle process you will not see. you will see that frequency at omega L, you are getting some kind of Lorentzian spectrum, and there is a line width, laser source, right? And it is happen inherently to every system. And what is the reason? The reason is nothing but I have discussed here. Sorry to go back. That is the reason is nothing but half H cross omega. So the ideal system is not possible because in the nature itself, you will always find that a spontaneous emission will be there in the system. So when we talk about any amplifier or laser system, it starts from the noise, and noise system explained from the half cross H omega, like 0 point energy, they will say in the physics. So once you understand that, okay, if you have the, let's explain by this. So if you have the laser source, and I have written in the Glover notation, P alpha alpha conjugate, it is a Dirac notation. You can see the Dirac function. So it is a, if you say ideal laser, I will have a straight line with a time t. If you see a time t, I'm plotting with respect to time t. If time t equal to 0, you have a, when the laser is a very ideal condition, it is alpha alpha conjugate. So mod alpha square is total number of intensity, and the photon, you take the count, it has the probability distribution function is a Poisson. Sorry, it will be e to the power minus its average n, mod n value will come. So it means that if you have this alpha alpha conjugate 0, so this state is a coherent state, and the photons coming from the ideal laser, it follow the Poisson distribution, right? And this is the ideal coherent state, and the Nobel laureate by the Glover, he have solved that. But in our case, we form the laser, it have the phase noise, it have the intensity noise, right? And then how it is happening? But if you see that at time t equal to tau, you will start getting Gaussian. Then it will go to the optical channel, it starts getting more spreading with respect to time, right? And this analysis, how can you do? By degree of coherence. So for degree of coherence, if you calculate here t plus tau, and once take the autocorrelation, what the value will come, take the Fourier transform, you will observe this picture that what we are written here t plus tau. So before now we are starting with our current optical link, just I will recall what is the goal of my talk, to make you to feel that there is a coherent quantum picture of our coherent optical link, and there is a classical picture of the coherent optical link. And when it is said as a semi-classical picture, and when you will say it is a fully quantum picture, where we can apply quantum and where we can apply the semi-classical picture. So just there is a, to explain that, I have taken this comparison basis set, like I have talked to you like a density operator. Here you can see Pn represent the probability of number of photons, and n is nothing but discrete value of number state. Like for energy level, for En energy level, what is the value? N plus half h omega. So it corresponds to that energy level. So it is a discrete value, and it is a single number state. When you say hit n, it is a single number state, and diagonal representation. So if you have noises, it will come in the off diagonal. We assume that if there is no noise, it will be, can take the diagonal of the matrix. So it is a P of n, the probability of number Pn, what is the probability of finding n photon in the given eigenstate. So when you talk about number state, when you talk about 2 photons, 3 photons, 4 photons, you are going to talk in the eigenstate n and n. So this is a pure discrete value, and you can say the pure number state discretization, it is a quantum picture, right? When you talk about 2 photons, you talk about quantum picture. When you talk 3 photons, you will talk about the quantum picture. But if you talk about 10 power 6 photon, 10 power 4 photon, 1000 photons, right? Then it will come in the classical picture. And that also the Glover and Sudarshanan, that is Sudarshanan from our, he's from the Chennai and the MCT college, and he, both of them, they have given this representation. And this representation makes all the quantum explanation for our things very easier. What it means that anything in the density operator, any eigenstate, we will converge to the P alpha, mod alpha, and odd alpha, means that you can write in the terms of coherent state representation. Coherent means ideal state of representation, you can write it, right? And the alpha is the current state. We know that every current state is via a complex quantity. We know that how the discretization A acting on like creation ladder operator acting on alpha, how the photons are created, and we know the probability distribution of P alpha, and we know the current state can be transformed to the number state. So this is the, you can say the medium, the current state is a medium. I can say the Ehrenfest limit, you can say that this is a classical analysis. So when you take the average P alpha over a current state, it will say you semi-classical picture. When it you convert current state alpha into number state, it is a quantum picture. So it will simplify very easier to convert semi-classical picture to the quantum picture. Okay. So I hope the above this talk, the takeaway point is there. We in optical link, we have I will explain the first this. So we have the quantum picture to solve our optical link, and the semi-classical picture is there to solve the same problem. But when you talk about the lower number of photons, like single photon state, entangled photon state, or higher number, the few number of photons, then this my quantum picture, like a current state into eigenstate of n, will be able to explain very clearly to the quantum theory, whereas when you talk about the intensity, where the total number of photons doesn't matter, then it is a semi-classical picture is very, very important. So I'm going to talk now about optical, how this, whatever we have studied now, how it can be applied in my frequency coded quantum key distribution system, heterodyne current optical link. All right. So just for overview, I will go detail one by one. So you can see here laser, right?
And there is
So
a question, sorry for the interruption. There is a question asked by Anandraj sir.
okay, ma'am. Okay, ma'am.
It's in chat. You can complete the question and then
Yeah,
you can
ma'am.
post it.
Yeah, ma'am. Yeah. What is
Can
the
I
question?
read it? Can
Ma'am,
alpha 0.5 and beta of 0.5 have the same values in a qubit superposition state?
pardon, ma'am. Once more, can you repeat it? That?
Can alpha of 0.5 and beta of 0.5 have the same values in a qubit superposition state? You can check in the chat window.
Okay. If it is fine, I can. Is it fine, ma'am? I can give you the answer to end. It is okay, or can, because whatever I want to say here, you can. I think the question related to here. This is the issue with,
This is the first slide, he says, like.
Yeah. I think here, right? I think here, ma'am. Is asking in the case of superposition. I think the current state psi, it has the alpha 0 and plus beta 1. So only things we have to keep in mind that here mod alpha square, if it is 0.5 and plus mod beta square must be equal to 1. So whenever you are forming that, the normalization and the sum of the probability distribution should be give the addition to be 1. Right? So when you say that qubit means here the mod alpha square plus mod beta square should equal to 1. So whatever the value of mod alpha square is 0.5, then mod beta square will be the 0.5. So it can be. I think I have given the answer, or no. Yeah. No, sir, alpha equal to 0.5 and beta equal to 0.5. No, because you are talking about when I'm taking the probability distribution function. When you talk probability means this is the alpha acting on psi 1. So generally we talk about the average value. So you have to consider adjoint of psi 1 also. So it is a kind of wave function, like if you say the integration. So integration psi 1 x conjugate of psi 1 x conjugate, right? equal to 1. That is the orthogonality. Similarly, when you write the alpha for psi 1x, then alpha conjugate for psi 1n 1 conjugate, right? So it will be the when we're talking of probability, it should always talk in terms of mod alpha square. So you have written alpha is equal to 0.5. So when you do mod alpha square, the value becomes 0.5 whole square, right? And when you do mod beta square, 0.5 whole square, 0.25. So the sum will be not equal to 1. So it will be not satisfy our sum of the probability should be, it should be 1. So it cannot be. Sorry, ma'am. Actually, I planned for the written thing.
Yeah,
So
it's
sorry
okay.
for them. Actually, I thought that I can able to edit many things in our screen, but due to issue with my tab or something, I cannot able to do that. So if time permits, even I can come to college and I can get things if opportunity comes. Okay. Okay.
Yeah,
So what I want to say here, so in optical link, let's understand that what is the semi-classical picture of tensors. So if you have the laser, right, the inside the laser explanation today we are taking from inbuilt from the quantum nature. But output of the laser, the behavior of laser like electric field, we are taking in the classical. So that's why it is called semi-classical picture. The first part you should be very and then inside the behavior when you form the laser from the cavity, it is always discussed by the quantum theory. It is a very semi-classical theory fails to explain all the laser operating below threshold, after threshold, and whatever the Poissonian statistics. So I'm not going to detail. Just I want to say in optical link or any lasers outside is the classical picture, inside is the quantum, and that's why it is called semi-classical picture. And in our case, I have taken two examples, and what were that? Like a frequency-coded quantum key distribution system. In QKD system, we use lower number of photons, single photon state, entangled photon state. So there, my semi-classical picture cannot stay, and that I'm going to say you how it will be. Why will not say that will I explain in the heterodynamic current optical link. But let us see the example here. We have laser, we have phase modulator part here, and we have the RF thing like a VCO1. That is you can say the RF oscillator, and we are giving the data in respect to theta1, right? So theta1 correspond to, here I have used like V92 protocol, means bit 0 and bit 1 correspond to 0 and pi. And the RF oscillator have the frequency capital omega, that in the range of gigahertz, 10 power 9. Whereas laser have the frequency of in terahertz, right? And given to input of my phase modulator, and it is given to the channel, and after the channel once more going to the phase modulator 2, and with the help of optical filter, and we are seeing interferometer, that what we have correlation function, and we see the spectrum at the detector, and we calculate our performance of FCQKD system. And this part, transmitter part, and this is the receiver part, and the transmitter and receiver, we assume that both are synchronized, right? And this is say the Alice, and this is the Bob, and you can see that theta1, and we are using theta2. Theta2 also have a 0 and pi, corresponding beta bit 0 and 1. Okay, so these are the things that we, in the case of frequency coded quantum field distribution, and we want to know the performance, the quantum bit array, how for coherent state, what will be the my quantum bit array can be done. Second example that is very we are using in the current scenario in the case of direct coherent link and heterodyne. Here we assume the single phenomena. We have laser, we have phase modulator here, and we are using data given to the RF modulator like VCO1, you can see that. And after RF modulator, we are giving the information to this phase shifter, and giving the phase shift by 90 degree and this phase modulator, and dual drive. So it will act like this part, dual drive Mach-Zehnder modulator, we can use as here SSB modulation, single sideband modulation. And this is my optical channel I'm using. I'm using optical amplifier, photo detector, and then after photo detector, we are using band pass filter, and then we receive the data. So if what we want to say here, I am treating everything in the quantum. So we assume that laser already treated as a quantum, but output, how is the coming quantum picture? For that, we should know the first integral. Main important part is my phase modulator part. You can see here also is a phase modulator is integral part is there, and it is optical channel. We assume that quantum nature of optical channel we did not assume, and then we assume that okay, optical amplifier, what is the quantum behavior, and after photo detector is just like we assume as a photon counter. In the when you see the semi-classical, they will talk about intensity, mod E square. But here I will assume as a like a for me like a ball, that lights are coming as a particle nature, and how the data we are receiving and how semi-classical and quantum will deviate from each other. So if distinct technology, we know in the physics, they don't worry about the phase noise and all, right? But electrical engineer background, we should worry about the intensity noise created by laser, optical amplifier, RF source, and the intensity signal noise ratio will be not that much problem by using amplifier. But in the phase part is very, very important. So phase information, it is coming from the data, and it is going the phase noise coming to the RF modulator, and the phase noise coming from the RF laser source, and that phase noise created by another phase noise here to dispersion coming through the optical fiber, and how it is affecting to my final system. That is my work, and I will take with the previous way and then explain it. So I said that this is my phase modulator is a important element. So we taken the problem as ideal case. We assume that as you said, that inside the laser, it is a quantum treatment is happening, and outside also I am assuming that it is everything is in quantum, right? So I'm assuming that inside the electric field at the laser, and A, that is a field operator, and the eigenstate means if you have a single light, it will be generated by the current state alpha. But if you inherently, you will see that laser has a line width, and that is coming to my phase noise that I have already discussed before, if I talk. And that when you take the first order autocorrelation function, you will get the spectrum. And this is given to my phase modulator part. And the phase modulator part, once you give, and first we will read in the absence of laser phase noise and the absence of RF phase noise, what is my output? And then we solve that, okay, we will introduce the phase noise, and then we solve it. So how to solve it? Like here you can see in the previous, see like you can see VCO1, and here data like RF modulator we have, that is RF signals are coming to the here. So that is a V of T. We are having amplitude of VRF, and this is my modular capital omega frequency. You can see here that is RF frequency, where laser frequency is very at the 10 power 12, here 10 power 9, and zeta is nothing but phase matching condition, because the photons come from the laser with a different speed, and the field coming to the RF with a different speed. So this is taken care by phase matching condition. Then theta T is nothing but my data bit 0 and 1, and this is my phase noise attributed to my RF. So how to solve that? That's why I discussed that. This is we solve for our cases Heisenberg equation of picture, and interaction picture is very, very important. So I took the equation as a Heisenberg equation, whereas H total is written in the interaction picture. So H total is nothing but means what is inside in the phase modulator, what is my total energy of the system. So one is that if you don't give any signal laser, if you don't give any phase noise, what is my H naught? Once you on the RF modulating signal, so what will happen? My dielectric constant will depend upon this RF signal, E by ZT, right? And that will change my perturbation. Perturbation means it will change my existing Hamiltonian. Hamiltonian is total energy of the system. And that energy, so our aim is that, okay, I gave my field operator. I want to see that how this field operator evolving inside the phase modulator, and what will be the final field operator, and what will be the my photon statistics at the output of the spectrum, and similarly we'll see the spectrum. So that is a important thing, that okay, you have field operator input, what will be the my output, and if you given the phase noise at the laser and phase noise at the case of R. And it is very interesting phenomena aims in that okay, it's a starting point. The as you say, the discretization, you can see that this is my laser source, the photon at coming at omega L, and this is the gap you see from omega L plus capital omega, that is a RF field of photons. We cannot say the photon because we are considering RF as a classical field, but the appearance happens that both combined the photons are created, right? And if the RF field having the negative, the happening the destruction kind of that, this photon comes it means that here we interact with RF field, one photon created. And what is the probability of creation of photon? It is given by chi value, right? And chi is defined in terms of RF modulating voltage and modulator, like phase modulator quantity, and it is known quantity. Similarly, what is the destruction of photon? It is given by I chi conjugate, right? Mod chi square. Similarly, from this it is happened that from this place, like there also RF interacting, and the creation of the photon and destruction is continuously happening along the length of the phase of modulator. Okay, and finally at the end you are getting kind of thing like you will get omega L. I have taken as a spectrum, so you will get the photon at, you will get the sideband, infinite sideband. It depends upon my I and chi, the amplitude means how much is the strength of chi, that will be responsible for how many number of sidebands you have. According to theory, it should be the infinite number of sidebands, right? But it generally the chi value is very small. You will get only the first order, like omega L plus capital omega, omega L minus omega. But in the case of analog radio over fiber, right, we are using doubler, so we make the chi value high. So we use the higher order frequency here, right? So, and the probability of happening this photon, that is the sideband, is divided by, you can see here, J naught square by 2 kT, it comes from mod chi, and this is my probability happening at the omega L, and the probability of finding the photon, the first sideband, it is happening the J1 square 2 kT, and the higher of the probability. So here, that is a very, very important things what we got, the entangled state. You have heard that how to get the entangled state, and the phase modulator is a very, very important phenomenon to form the entangled state. So when you give the current state, you will get the superposition of how many current state? You can get 1, 2, 3, 4, 5, and this summation must be validated by normalized, and this sum will equal to 1. So if you change the probability at anything omega L, it can easily affect to omega L plus capital omega. So this is also called as a entangled state, and with a different frequency. Okay, omega, and this is a, in semi-classical, it is very useful as a COM source, right? So in our case, generally FC2KD system, we analyze phase modulator to generate entangled state or coherent state. So B and this A, B, C, all are interrelated, and you can decide what probability of the photon can fall to the other. So what is the output? We observe that, okay, when you have the laser cavity A, you have the quantum noise here. RF oscillator, we have a phase noise pi RF, and given to the phase modulator, you see that central frequency, right, at the center A is not affected by the phase noise of RF. Whereas the first sideband, DRF is get accumulated. Similarly, at the higher frequency, if you have the higher side of sideband, you phase noise of RF getting accumulating, getting added. So for current application, it is to avoid my RF noise kind of thing. SSB, I think it is a very good way of like avoid the noise system. So that generally we use single sideband, so that to avoid the other noise limitation. I will not go in detail, but to understand that the phase modulator is the integral part of my entangled state generation on other type of, even you are making other type of entangled. Generally in devices, we can generate entangled state, but in the case of optics, you want to generate entangled state, the phase modulator analysis is the important element. You should know the quantum theory. And I studied in the presence of phase noise, how the phase modulator, how the field operator behaves inside the phase modulator, and we got it out. And okay, once we done the phase modulator, how it can be applied to the QPD system, right? So what we have done that, okay, lasers we have, and we have the phase modulator one, and this is my RF data is given to the VCO RF source, and theta 1 and capital omega. So theta 1 corresponds to bit 0 and 1 given to the channel. I assume that channels are the lower length, so the noise arises due to the channel we are ignoring here, because since it is a pure quantum, lower number of a state, like we have a single photon state or two photon state, like kind of thing. So we avoid the ignoring the channel noises added here, and we use the same PM2. That's why transmitter side called Alice and the receiver side called Bobs. And the theta 1 is randomly chosen by the Alice, 0 or pi. Here it is also chosen by 0 and pi. And this is we use optical filter to consider only we want single sideband. We don't want we try to avoid omega L minus omega. We consider only the interference pattern at omega L and omega L plus capital omega, and that is given by interferometer. And detector will see my intensity, photon detector, how much it gets affected, and he analyze my detector. So let us go about the frequency QKD, and then so I will go to this tabular column. So tabular column transmitter, you can I have repeated LS, and this is receiver is Bob. So LS phase is we are saying B92 protocol. It means that we are assuming two phase conditions with a different frequency. So frequency correspond to we are having the lasers at omega L and the omega L plus capital omega here, and that is capital omega for RF source, and here also capital omega, right? So LS phase is 0 and pi, means theta 1. It corresponds to bit 0 and bit 1, right? And Bobs also can choose either pi or 0 or pi or 0, random phenomena, right? And then what it says that here, I assume that here no ifs are attacking, right? I assume that only the things happening only in the presence of phase noise. So this analysis I'm doing absent without phase noise to make you have given this existing paper. And then, so what we'll do that, Bob will do randomly choose, like means the function here, its intensity depend upon cos square delta phi. Delta phi means the phase difference between theta 1 and theta 2. So cos square theta 1 minus theta 2 will be, if you have a 0, we'll get a maximum interferometer. If it is pi, will we have a low interference like that. So Bobs also will choose randomly. If it is, he don't know that pi and he Bob choose by 0, so you will not get an interference. But if he Alice have like Alice transmitted 0, and Bob also with random phase he have selected by 0, so cos square delta phi 0, it will can detected 0. And if you call this also random phase pi, so cos square pi 1 means if you see Alice phase minus Bob phase, the difference will be 0, then it get detected by 1. Other case, you don't know. So we've declared by the detected by Bob. In this case, question mark we don't know, but if the phase matching condition happens, the Bob detected the phase. And common bit will be shared by 0 and 1. And so what is important here, the public channel, they have a secure public channel, and they will share the only what is the bit detected, either bit detected by 0 or bit detected by 1. And they know what is the random phase like 0 or pi or pi by 0. So that's why the results of Bob measurement, whether photons are detected or they communicated to allies, possibly through the public channel, but not the phase that they use. So phase they will use random, but only they will say in the public channel. That is also kind of thing, a secure kind of thing, that the bits got detected, right? So this is a without phase of presence of phase noise, and here what we calculate, okay, in the presence of phase noise, there is a V is a parameter that the effect comes due to the my laser line width, that is DLD, laser line width, and DRF is the phase noise of the RF oscillator, and this is the signal. If you see the P signal exponent, it depends upon the total number of photon count at the detector. But if you have here B, we have some value, right? So it means that QVR value will get it will get decreased. If V value is higher, my QVR will get decreased. So what it means that when we are analyzing the performance of frequency coded content distribution, we should always keep in the fringe visibility the important parameter that taken care of by what will happen, because when you have a two signal like a cos square delta phi means the L is transmitted at theta equal to 0, bit 0, and Bob also received theta equal to 0, 0. So this delta phi becomes 0, cos square delta phi 0, right? So maximum number of photons you will find. But if you have phase noise, the photons count will be, a spectrum will reduce, the intensity will get reduced, and that QVR, quantum bit error rate, will be, our performance will decrease, because already the intensity is a single photon. If the phase noise also affecting, my performance will get reduced, right? And that's the impact we have seen, and then we are publishing the Joseph D. So here, if you see the further application, we can apply intensity noise. We can use the another phase noises due to the channels, and we can enhance by thinking like what will be the ifs attack. So if you have the other Alice and Bob, and if you want to attack in the what are the different type of protocols, we can be used by if to detect the information. So that part is open for us to explore, and we can do in the FCQKD system. Next is the another important topic is just I think with time constraint, I'll go somewhat fast. But this is another important thing about current optical link. Here we are using laser source. We know the quantum nature of laser outside. We know the phase modulator here, and we know the here with the help of this data RF modulator, we are generating single sideband, and we are giving to the quantum nature. We are already existing in the literature without phase noise. So I have studied in the presence of phase noise, what is the optical amplifier behavior, and we have seen the photodetector and the data. Here I will show that my aim is to explain here outline that we can see how the field operator evolved inside our channel from transmitter to the detector, right? So here what we want to say that in the terms of picture, you can see here, you have the L here, and this is monochromatic picture. I am not talking about a spectrum I have drawn. I have just taken as a case of to understand it here. Here L at the fact, if you see that we have the laser phase noise, and A is my field operator like electric field, and it has the phase noise of laser line width means DLD. And similarly, you have the RF modulator. You have a theta t, that data either 0 and 1. Similarly, you have a phase noise of the RF modulator. It is coming, and here we are at the output of dual derived Mach-Zehnder modulator. You are getting single sideband. You are getting at the center, and L+1, the first sideband. You are getting the laser phase noise at the DLD, and the first end you have a laser phase noise and RF phase noise. Now it moved to the optical fiber. So what will happen is the frequency at L and frequency at L+1, right? It moved with a different different group velocity, right? So the time delay it is taken by this, I assume the tau plus, and this is a tau minus, right? So suppose it might be the one of each other, it will take the more and less time, right? So tau plus and tau minus means what I'm taking that L plus 1, if it is reach the length, 50 kilometer fiber or 20 kilometer fiber, it have the some differential delay happening due to that this frequency component will move faster and this frequency will move slower kind of thing. And it is given to the optical amplifier. And optical amplifier is a quantum treatment done by Metcozy. Another great thing that, so optical amplifier, the output should come such that M decide by the bandwidth. So generally, if you have optical amplifier, it have the infinite bandwidth. But in our case, we need the bandwidth such that it cover only to L and L plus 1. So it decides that if you have M equal to, means you are having the very good filter, optical filter, means you can see that V optical, that is optical filter bandwidth, and T, the multiplication should come 1. And P is nothing but polarization. So your data transmitting, X polarization you are transmitting, and bipolarization transmitting. So the value of M depend upon that, and the value you will see how M also affecting to our intensity and the phase. So just I don't want to go to the detail, but I want to make you to show that okay, I just analyze how the optical filters, as I said, how the field evolved inside the optical filter, and the similar analysis we do Heisenberg equation, Heisenberg equation operator, and as well as Schrodinger picture. And now the most of the problem can be solved by the Glover density, that Glover density, phase density function. So we assume that here what is my field operator coming to the optical amplifier, what is falling at the photodetector by this equation. So here first part they take is the laser part, coherent part, and this is the NAC, the noise coming into the optical filter kind of optical amplifier. And this my field operator take consider both coherent as well as amplifier part. And the another thing, the important thing that whenever we are saying in any each link, Heisenberg uncertainty must be satisfied for the link, because in the electric field you can write electric field for omega multiply omega plus capital omega, but in the quantum you cannot do that. You should satisfy AL, like here I have written right ALA, and so this commutation relation for the single mode. Similarly, the L plus 1 mode, it must satisfy the Heisenberg uncertainty. So then only quantum picture will give the complete detail for. Now, in the case of semi-classical, you find the intensity like E and E conjugate. Here we will take the electric field operator and conjugate of that operator, and the ordering is very important. In the case of semi-classical, you can write like this, and mod U square you can calculate. But here you can operator there, and this will be give me the average number of photons. But the same time, what will happen? My omega L and the center frequency and first advance move with a different time delay, and this phase noise of RF part come in the picture, and the differential delay due to the length of the fiber, the phase noise come in the picture. So that I have written tau naught, tau plus minus tau naught, and this is nothing but S is the chromatic dispersion and wavelength. So another the phase, the noises we got now RF, we got noise due to the laser, and there is a dispersion happened due to the channel. And that channel we have calculated the variance, and the variance is very standard format we calculated. But the new thing what we have calculated, we have the radiation length, but the variance in phase also affect in the intensity. So that taken care of my this chi, that how this phase also it affect in the chi. So this is the basic detail what will be, I was saying that suppose you have a M value, you can see that M equal to 2, M equal to 16, another part of, so I have given here semi-classical picture and quantum picture. So what I want to say here, if you want to calculate the direct detector, I want to calculate the intensity at the detector. So we can calculate a semi-classical that already we study in fiber optic communication, all standard book. We go from the BER semi-classical. There what we'll do, we will calculate the intensity distribution, and we calculate the this formula, we substitute for 0 and 1, and the semi-classical probability distribution function will give me the answer. But if you consider the photon number 2, 3, 1, that this distribution will change. So you can see here, you have modified Bessel function m minus 1. M depend upon your filter, optical filter bandwidth and receiver bandwidth. And here you see it is a log-1 polynomial distribution function. So when it both will get converged, when you increase the number of photons, we'll see that exactly converging at the both distribution is converging. So at that point, we no need to study about the quantum. But if you want to study the quantum, if you see the gain, like 3 number of photons and 4 number of photons or lower number of photons, you have to give extra penalty of number of photons. So what it suggests that even if you are calculating the lower number of photons for direct detection, we can go only photon counting distribution becomes easier. Or the BER. If you want to calculate BER, we have to calculate P1N and P10 in the quantum picture. So this is the direct detection case. And now you come for the current detection case like that. So this is this slide very, very important that whenever we write in the semi-classical picture, we in detection we know current means we detect at the theta, right? So we have the always joint probability distribution function. Mod beta comes to the strength, that is R, and theta. So generally, if you want to probability take R, suppose I'm saying, so if you want to take P of R, so we will integrate with respect to theta. But here I want theta. So in semi-classical regime, what we'll do? The marginal probability distribution function they will calculate by assuming this is P mod theta, which integrating with respect to mod beta with respect to R, and give me my P theta. Once I got P theta, I can calculate the bit error rate, right? But in the case of quantum, we can't do that. We follow the same procedure, but we want to write P theta in terms of basis representation, the discrete number of photons, right? So it is like when you write phi, it is like a n plus 1 conjugate. You will write the number of photons n and n plus 1, and this my e to the power minus I phi will give my phase information. So like a quantum phase distribution, we have semi-classical single probability distribution function. You have only same P of theta. But in the case of quantum, you can use Wigner's quasi-probability distribution function, coherent state representation, and other many different type of other quasi-probability distribution function exist. But Wigner is very easier to solve that, right? And what we observed that I calculated the quantum picture and then I calculated the variance, like delta, how the variance, like how I told you that M equal to optical amplifier, if change M equal to 1, 2, 3. So if your optical filter is not very good, then my uncertainty in the phase will increase. When you are exact very ideal filter, that it exists our given bandilla that optical amplifier paper. And similarly, we calculated chi with a different phase noise part, and we see the variance. And just for this is a more equation, just I want to have a feel of that. So this is my quantum treatment of bit error rate, and you see here it is a classical, semi-classical for phase information. So this probability distribution I'm talking about phi, not in the intensity. So I need to see that it talks about discrete k and k plus s, but here it talks about I of s. It is like a modified Bessel function, but it talks about the discrete eigen number state, like of basis representation. And what is the CK? I have explained here, like how like the coherent state representation, and that's why Glover representation become very important. And what I found that in quantum treatment, the phase will get affected by chi, that is the amplitude coming from the phase part. But in the case of semi-classical, we have no chi term. So I learned from the quantum and then I applied to the classical by our intuition. And what we saw that it's a both quantum and semi-classical picture get matches, right? Both picture it gets matches. Even then we got the doubt that, okay, when you have our quantum for 2 bit error rate and here semi-classical, the nearly we are getting same, but when you introduce the chi, when you introduce the chi, in absence of chi, you can see the relative error decreasing as number of photons increases. So what we thought that it is nothing but the deviation in the quantum and semi-classical picture, but it is not true. It is happening due to the numerical precision of our mathematical that software we are using. So even it look like the relative error when increase like a random kind of thing that initially is high and slowly when number of photons are increasing. But what we found that no, it is a semi-classical picture and quantum picture for phase analysis are giving the same answer. Then the question after that, when we can, now we have considered the current state, but when you want to give the bit error rate, like in the case of now we are using entangled state, and I want to minimize the bit for lower number of photons. So we are using a squeezed coherent state. So a squeezed coherent state, we cannot solve by the quantum picture. Why? Because there is a P alpha, whatever I have discussed, there P alpha is a negative value. And semi-classical picture will never discuss about whatever the P alpha value for the negative value, how it can be solved. And what is the importance of coherent squeezed state? Like you can squeeze one of the states. Like if I want to transmit the data in phase, so what can we do? I can squeeze in the phase. I can enlarge intensity in the intensity fluctuation in the intensity term, and we can transmit it. So there, what we feel that okay, the semi-classical picture will not work. So we need to do the quantum treatment. So that can be the further work, and all the photonic links can be done. Even the CV2KD link, what we are doing, we are using coherent state representation. So the continuous variable quantum field distribution system. So now we are transforming to the squeezed coherent state distribution. There, my semi-classical picture will not work. So there, we need to solve the quantum picture. I think. Thank you, ma'am. I think I did not take more time. So.
Thank you so much, Rana.
Yeah, ma'am. So first of all, I want to say sorry, ma'am. Actually, my plan was something to be. I want to write and show some diagram and block diagram. So I presented with like that.
Okay, Rana. It's
okay.
Any questions from audience? From my point, I just want to ask one question, Rana. Like, how do you simulate, and what was the tool that you used for getting that simulation for checking the bit error rate as well as the
I just solve the mathematically all the Heisenberg equations, right, ma'am? And then we will do in mathematics. So I did not use any simulation software like what was existing in there. Many software is we are, but we use like our analytical results, and then we put in the Mathematica and to see the analysis. So it is totally based in analytical results, you can say.
Tool used was Mathematica. That's what.
Yes, ma'am. That's of Mathematica.
So we will wait for 2 minutes for if there are any question from participants, else we'll invite it.
Yeah, ma'am. Stop.
Sir, what do you mean by casualty induced phase noise, sir?
Pardon, sir. Actually, tell me, sir.
Casualty induced phase noise.
It is in my
casualty induced phase noise.
What induced, ma'am? That is first part. What is first word?
Sir, can you please type it, Arvind sir?
Yeah, ma'am. Yeah, I can say so that first word I didn't understand.
Yeah, that's what. Arvind sir, can you please type it? Yeah, he has typed.
Yeah, ma'am. I don't know about casualty induced phase noise. I don't have an idea, sir. What it means casualty here? What you are saying casualty here?
Actually, I just seen some disadvantages of the same.
Casualty means like you are saying the P alpha negative value or something. Casualty I didn't. Really, it is not audible for me. Ma'am, it is not audible what sir has explained.
No, he has typed it like casualty induced phase noise. He have seen it somewhere as a disadvantage. Is what I'm
Ma'am,
telling is right?
Okay.
Aravind
So
sir?
I don't know. I have to
Anisha, can you please mute the participants except Aravind sir so that he can post
Yes,
the
ma'am.
question?
Yes, ma'am. Yes, ma'am. Done, ma'am.
Aravind sir, you can unmute your phone and you can ask your question.
Yes, ma'am. I just send the disadvantages of the same. I just want some clear idea of it.
just I will opening that. I just will check that. Quantum computing from unit algorithm and you send me the document, right? Actually, sir, really, I don't know about cognition this page noise. I will go through that and then I can say to you. Or actually, I don't know about that. How it is.
Okay. Sure, sir.
Any other questions? Okay, then we can wind up this session.
Okay, ma'am.
Thank you, Dr. Rana Pratap, for coming
Please,
and giving this wonderful insight about quantum theory, especially quantum statistics. It's great to see you like after completing ME optical communication, you have having a deep insight on quantum physics. As an overview, what we understood is that how the bit error rate is getting minimized when you are trying to use the quantum instead of your semi-classical thing.
Yes,
And the frequency coded quantum key distribution, already we heard one of other speaker telling the same Alice and Bob, and we found it useful while you were explaining about that. And one another thing what I found out is like you mentioned about the Nobel Prize that has been won in this phase-space probability distribution. That's great to know. The way you have presented is very clear, and the PPT presentation was very neat. Thank you, Rana, and thank you for being with us. Hope to connect you later with us.
Yes. Thank you, ma'am. Thank you. Thank you all for.
I thank you so much. Manjia sir, are you there? Okay, I would like to thank Dr. Manjia, who is another speaker who is also joined us for both afternoon session as well as the evening session. Out of curiosity, he's a very eldest resource person that we had in our ATAL FDP on quantum computing, and happy to note that he's curious and interested in learning much more by attending the other sessions as well. Thank you all. And I just want to, before concluding the session, I just want to tell the participants that tomorrow the session starts at 2 o'clock. I want to remind you like the 11th session and 12th session will be handled by Dr. Manjula Gandhi from CIT Coimbatore on quantum algorithm. And the 13th session, the last session will be on quantum circuits and VLSI design by Dr. Ramagowda Dinesh, Samsung Bangalore. And then we will be having an online test and the feedback, overall feedback. So that will be happen between 6:30 to 7:30 p.m. and followed by the valedictory section. So please be make yourself available for the attending the 11th session at 2 p.m. tomorrow. So thank you all. Fatima ma'am, we have recorded for sending the recordings to AICTE. I'll have a word with the coordinator and I will let you know. Is it okay, ma'am?
Okay, ma'am.
Okay, thank you.
Oh,
But
the
I have
PPT
shared up to this session, whatever the PPT or PDF that we got, we have shared in that folder. Hope you
Okay.
can access that.
Okay, ma'am. Thank you, ma'am.
Yeah, thank you. Anisha, we can wind up the session. Thank you, Rana. Thank you,
Okay, ma'am.
Manjaya sir,
Okay.
and all the participants and my team members. Thank you.